and we have a spring.
Okay.
All right, and so we need to define a 0 point, a reference point. We could define way up here. We could define the reference point way up here. Problem with that is if we do that, if we define it way up there, then we have to calculate the length of this spring. All right. So you can do that. It's fine. It's just the equation becomes a little bit different. If you choose this to be x equals 0, so if you say, hey, x is equal to 0 here, then as this thing bounces up and down, then it looks like this. So you get, and this is not with any friction yet, okay? But if we do that, let me make this a little bit bigger here. We get that the acceleration is equal to minus your spring constant times x plus all the weight, yeah, divided by the mass. Okay. So that's if you choose this red line to be your x. On the other hand, if we choose this point up here, about the length, okay, so then you your acceleration is equal to minus ks times the length let's see, that's the length it's like basically x minus the length, okay, plus the weight divided by the mass. Oops. All right, so this is kind of the issue that you get into depending on where you define x equals 0 at. Okay, if you define it up here, then you have to deal with this length of the spring. But if you define x equal to 0 down here, then it's exactly the same thing. It's just a little bit simpler. All right, but this is your acceleration here. And then, of course, you have to put in your k terms in there. This is, for every step, you would have x of k. You'll get like the acceleration of k is equal to minus times x of k minus 1 plus the weight. All right, so that would be your acceleration term when you think about the time step. Okay. All right, and then so now all you got to do is integrate. Okay, now this is without the bungee cord piece though. Okay, so then this has no friction in it. But then you simply integrate, so you have your velocity at step k is equal to the velocity that you had before plus your time step times your acceleration at k minus 1. And then your position x then becomes x of k minus 1 plus the time step times the velocity of k minus 1. So, that's just a given. So the only thing that changes when you start considering bungee jumping or anything else for that matter is friction. So so now you have to calculate your friction. So this term here, now that I just put that there, let me widen it over here. So this term here, we need to add in the friction piece. Okay, so the friction, then we would have to subtract off our friction minus 0.65, if I remember correct, times the velocity. No, wait, there's area. Times the area times the velocity. So I'm going to run out of room here. Okay, so it's going to be times the velocity just trying to clean it up here. Let's try it again. All right, so we're going to have the velocity of k minus 1 times the absolute value of the velocity minus 1. And the reason we do this absolute value here is because velocity is going positive and negative, and we always need to make sure that we keep the sign, because velocity is going in the opposite direction to our motion. Or, excuse me, not the velocity, but the force, the friction. Shoot, I'm missing my well, no, 0.65 times the area. That's my, yeah, that's my K piece. All right, so this piece here now is the friction. Okay, so that's going to slow down the system. Okay, so you start off without this. So if you take this away, you have what we call an undamped system. So the system's just going to oscillate back and forth, and it will look like this. All right, and so this is what that will look like. And let me edit this for a minute. All right, so I'm going to take away and I'm going to increase my time. Where's time? All right, so this is my oscillation, okay? And so all it is it's just bouncing back and forth, bouncing back and forth, bouncing back and forth, and it never decreases because it's just oscillating. It's what we would call perpetual motion. So if you ever figure out how to do this, you know, and get perpetual motion out of your Monte Carlo, is it? You know, that's where the money is, right? Because perpetual motion, no friction, the thing just keeps going, right? You don't need all that gasoline.
Yeah.
And so this is undamped. But then when we add in the friction, we add in this friction piece here. Now the system is going to slow down. So if I come in here, let me save this file. I'm going to add my friction in here. So my friction now, here's my acceleration term, x double dot. Okay. And then I need to add in the friction. So 0.65 times the area. I don't remember what the area was. Just make up a number for right now, times my velocity, which I just called my velocity x dot. All right, and so got an error message. Just have an extra parenthesis or something here. Missing one, that's it. Okay. So see, now the system's decaying. That's the friction. You see how it's going down now?
Mm-hmm.
That's so it's being it's decaying. So if we extend our time out, where was time here? If I extend time out to, I don't know, 25 seconds or something, it's getting smaller and smaller and smaller. Where if I take that piece away, the thing stays constant. It never gets smaller. This is undamped. and this is damped. So it's decaying. So now if you want to do a bungee jump, okay, so what I'm going to do, I've got all this. These are my initial conditions here. I didn't label them. But now I'm going to add the bungee jump. Okay, so what I'm going to do is I'm going to copy these, and I'm going to relabel them B for bungee. Because I want to plot the two together so that we can see the difference. Okay, so I just took all my initial conditions, I just doubled those, and now I'm going to take this, and I'm going to copy all this, and I'm just going to, anywhere there's an X in here, I'm going to make it a B. Oops. Did I miss any? Okay, so these ones here are at 40, 41, and 42 are my bungee. And so what I'm going to do before I go any further, okay, so I'm going to plot this. This one's going to be red, and then I'm going to plot my bungee and make it blue for bungee. And I just want to see the two. Now, right now, they should be right on top of each other. So you see there, they're right up, red and blue is on top of each other. So I've got purple. All right, so now what I'm going to do, though, is inside, I'm going to create an if statement here, and I'm going to say if X, or B, because B is my position for the bungee cord. So if B is less than 0, then I'm up above that. So if you I forget which, I think it was this one maybe I had the link to. All right. Oh, that's a perfect picture there, actually. You see this bungee cord tied to his feet? You see how it just loops around here? So let me paste this in here somewhere. All right. So if you look at this, right, you see this bungee cord here? He's flown up past it, so there's no tension in it. So there's no force in this rope. Okay. And so since there's no force, that goes to 0. So when he's up above there, that goes to 0. So that's what I'm going to do here. So when that value is less than 0, because remember we defined down as being positive. That's why it's less than 0. So if it's less than 0, the spring or the bungee cord, all this disappears. And you're just left with the velocity, the friction piece. All right. And then otherwise, you have the same thing that you had before. And so now if I plot these two, whoops, that didn't work. So the bungee cord zeroed out on me. Well, I'm not sure why it did that. Did I get an error over here? Ah, I'm getting an error. Oh, well that's just a graphing error. That's from down below. That's not a problem. So my bungee is not changing. So what did I miss here? B is equal to 0. BD is equal to 0. I'm missing my weight in this equation. I see that now. Okay, so plus the weight. Do I have the weight defined? So this should have a weight piece in it too somewhere. There we go. So you see that they're not quite on top of each other here. I probably need to be cleaning my figure. I am cleaning my figure. Why is that? Okay. Oh, they're just so close together. So you see they're no longer on top of each other because with the bungee cord, you're losing force. So you're not going up quite as high because the friction's kicking in, but you don't have the spring pulling you up. So the red is with a spring pulling you up, but the blue is with a bungee cord, so it's pulling you up as long as you're down below the length of the cord, the default length of the cord, but then it's not. All right, but so this if statement here had to come into play. So we added friction. This is air friction here. And then, and again, this here is exactly the same, except for it has the if statement that if you're above the point, so you have all this slack, so there's all this slack in the rope, you have no tension, the rope's not pulling against you anymore. So therefore, that's what this if statement is for. So you just had to add the if statement. Once you had the damped spring working, then you just add the if statement to say, hey, if we're above that, and then you see there's just a slight difference. It's not a huge difference, but there's a slight difference there. And there's your bungee jump. All right. And if you run this out, now one thing I need to say about this here, when you look at this, it hasn't settled down yet, right? So this guy on the bungee string is still bouncing around. So what we need to do is we need to run the simulation for more time. So right now it's like 25 seconds. So, I might need to run this for 80 seconds or maybe longer. I don't know. You just run it till he settles down. Okay, so you can see there he's still bouncing around, but he's not bouncing around very much. All right. Another thing is if the friction increases. So if we go to our area, I just hard-coded the area to 4. I'm going to make that a variable, and I don't know, make it 8. So I'm going to double the area, my cross-sectional area. I typed in the word 8. It should be area. All right. So if you increase your resistance, then he settles down much faster. Now he's still bouncing around like mad. He's going to bounce around for a while, I guess. But, but those are the factors that are going to affect your plot. All right. So, but your acceleration, remember that we're applying Newton's laws. So when we look at Newton's laws, we get Newton's second law says that the forces acting on a body is equal to the mass times the acceleration. So his first law says that a body in motion stays in motion, which means that the acceleration is zero because the forces are all equivalent. All right. And so if the forces are not equivalent, then this second law is what satisfies the third law, basically, is the fact that the extra force due to the acceleration is in here, which is due to the mass times the acceleration. Right. So I guess basically, if you think about getting in your Monte Carlo and, stepping on it and peeling out your tires, and you feel that force pushing you back into the seat of the car, then, that's this second law piece here, that acceleration, that force that's like pushing you further down into the seat as you're flooring it. So does that help any?
A little bit, yeah.
I mean, I'll post this video. I'm recording this, so I'll post it so you can go back and watch, and you can look at all the codes in there. I did notice that as I was working with that code, I noticed the weight wasn't there. I'm like, that doesn't seem right. So just a little story for you. Years ago, many years ago, my friend, I think he just turned 18, and we went out to this one bar. Actually, I guess it was a bar. I wasn't even 18 yet. He was slightly older than me, and we went out and was at this bar for a while, and then we're coming down Lincoln Way. You know how Lincoln Way runs into Tusk there?
Yeah.
And Massillon. Yeah. We were coming down there, and it was actually another friend's dad who was driving, and he actually had a Monte Carlo. And we were driving down there, and this guy, I don't know what car he was in, this guy pulls, into the lane, it's two lanes there. And he's like revving his engine. We're sitting there to like a stop sign, and he's like revving his engine or whatever. And so my friend's, the light changes, and my friend's dad floors it, and we're like flying down Lincoln Way, at I don't know what, midnight or something, late at night, going down there racing, sort of racing, it's like, I'm sure they got above the speed limit at the time, but racing his Monte Carlo. It wasn't really anything special, it just was a stock engine and everything. And
Yeah.
But
I've gotten mine, and he still got some get up and go.
yeah, it had some get up and go. Yeah, and like you say, I mean, it's not like we were doing 100 or anything. We're probably maybe doing 45 or something top. I don't know. Maybe they hit 50. I don't know, but I think it's only 35 down through there. But
That's the Lincoln
I'm
Way.
pretty. I'm pretty sure they had topped this, went past the speed limit by at least a little bit, but you know, that was 35, 40 years ago.
Yeah, you can't
Different
do that.
lifetime. Yeah.
At least not on Lincoln Way.
Yeah. Well, and yeah, it's like, you know, I mean, we made when the light changed, and then we were able to go through quite a few lights before it, you know, we finally hit one that was turning red again, and you know, of course, he didn't run the red light because it's one thing to be speeding down the road; it's another thing to run a red light when somebody might be coming the other way.
Yeah.
So. All right. So anyhow, that is the uh, you know, that's Newton's law, okay, and we're just applying Hooke's law, and which is proportional to the stretching of the spring, and then we have, of course, air friction, and yeah, if you look at the other set of slides, you're right, you can calculate friction a couple of different ways, but your book for the bungee jumping was using Newton's air friction. So that's what I used here.
All right.
So, but yeah, I mean, this should all be in the book, but like I say, yeah, I mean, you said you got that diagram, but I don't know. His model diagrams, I honestly don't find them overly useful. They're too complicated. All those circles and boxes with arrows pointing 8, 10 different directions. I don't find those real useful, but
Yeah. So is number 3 gonna be pretty much the same thing then?
number 3.
Yeah.
Which one's number 3? I don't have it in front of me.
Oh, sorry. The creating a simulation of 6.
426.
Yeah, 4.2.6.
426 was the diagram of the bungee jumper.
Yeah.
426 or 326?
4. It says 426. Blackboard. It says question 4 on page 86. Edition.
Shoot. I don't have question. What's question 4 say on page 86?
Let me see if I can grab it right back here. It says, with down being the positive direction, give the formulas for each of the following components of the diagram for a bungee jump from figure 3.2.6.
Yeah.
I think you meant to write 3 and not 4, but I wasn't entirely sure.
I meant 3. It's
Okay.
Yeah, I'm sorry. He changed the chapter numbers. It was chapter 4 in the first edition.
Oh.
So I guess I need to edit that.